In September 2002, astronomers discovered an asteroid in an unusual orbit around Earth, which surprised them considerably because, as far as they knew, the only natural object that orbited Earth was the Moon. And so this strange object couldn't be an asteroid but had to be something that was made by humans. As it turned out, this was in fact the Saturn V third stage, which launched the Apollo 12 astronauts to the Moon, a rocket component that left Earth in 1969 and went on an extraordinary journey unknown to everyone before returning to Earth 3 decades later. Understanding what happened to this rocket and why it ended up on such a peculiar journey requires examining how a tiny error in the Apollo 12 mission sent this rocket stage on a 30-year trip through space only to mysteriously reappear on Earth. The Saturn V rocket had 3 stages, with the first stage burning for approximately 2.5 minutes and getting the spacecraft to an altitude of 61 kilometers, while the second stage would burn for around 6 minutes, taking them higher and faster, and then it was up to the third and final stage to do a short burn and get the spacecraft into orbit. Once it was in a stable orbit, the third stage would be fired up again to perform the translunar injection burn, sending the rocket and crew on a trajectory to intersect the Moon. And once the Apollo crew were safely on their way to the Moon, the third stage would separate and NASA would attempt to discard it. On previous Apollo missions, they aimed to place it into an orbit around the Sun where it would remain for thousands of years, and in order to get into this orbit, NASA aimed to meet the Moon on its trailing side, where the Moon's gravity would slingshot the rocket away from Earth and into a solar orbit. For NASA, an orbit like this represented a good investment because it meant the object wouldn't get in the way of future missions, but things didn't quite work out as planned for Apollo 12. In order to get rid of Apollo 12's third stage, NASA had to set it on a path to meet the Moon at a specific location. But the initial trajectory had it headed toward the wrong side of the Moon, and so the third stage needed to do one final maneuver to change its trajectory. In order to complete this maneuver, the third stage used its auxiliary propulsion systems, which were 2 sets of thrusters at the bottom of the stage that provided yaw, pitch, and roll during flight, and despite having to change its position by thousands of kilometers, it actually took very little energy, since changing its trajectory so early in the journey would have a big effect once it reached the Moon. At the time of separation, the third stage was traveling at around 20,000 kilometers per hour, and in order to change its trajectory it had to slow down by about 140 kilometers per hour, which would delay its approach to the Moon, making it arrive at the opposite side. NASA completed the maneuver, but unknown to them it didn't go according to plan, as the entire Saturn V rocket was controlled by the instrument unit located above the third stage, which had its own internal guidance unit on board that was used to plot the rocket's trajectory. It also had C-band transponders which would send signals back to ground stations on Earth, giving NASA more accurate trajectory data, and once the rocket was safely in orbit, NASA could compare this data with the rocket's own data and see if it was following the desired flight path. If anything was off, they could send a command up to the rocket to correct it. But what NASA didn't know was that the tracking system was out by a tiny amount, which led them to believe the rocket was traveling faster than it really was. And so in order to get it to the target velocity, NASA ended up slowing it down too much. They overcorrected by just 40 kilometers per hour, but this was enough to drastically delay its arrival to the Moon, causing it to miss by thousands of kilometers, and so instead of being thrown out into a solar orbit, the third stage ended up in a highly elliptical orbit around Earth. Over the next 15 months, the orbit was constantly stretched and pulled in different directions by the Earth and Moon's gravity, getting stretched all the way out to Lagrange point 1, which is a point between Earth and the Sun where the gravitational forces of both bodies cancel out. Once the third stage passed beyond this point, the Sun started to have more of an influence, and to understand this phenomenon, imagine a steep hill with a car trying to reach the top, where if the car doesn't have enough velocity to reach the top, the hill will drag it back down to the bottom, but if it has enough velocity to move past the top, it will start to get pulled down by the other side. This is exactly what happened to the third stage, as it passed the Lagrange point 1 hill and was now being dragged into an orbit around the Sun. And in a way it finally achieved what it was meant to achieve. But this orbit around the Sun was far from stable. Instead of being accelerated to a solar orbit on the outside of Earth, it had been slowed down into an orbit on the inside of Earth, and because of this, the third stage was now completing its lap around the Sun a little bit quicker than the Earth, which meant it was slowly pulling away. However, it was only a matter of time before the third stage would catch back up, and this actually happened in 1986. But it wasn't quite close enough to the L1 point, and so it never got pulled into Earth's orbit. And the third stage carried on racing around the Sun for another 16 years before the inevitable finally happened. In 2002, the third stage reached its apotheosis just as the Earth came onto the scene, and this time the third stage crossed beyond Earth's L1 point. And for the first time in 32 years, the Earth now had more pull on the object than the Sun. Over the course of 2 months, Earth pulled the third stage into a highly elliptical orbit around the Earth just like the one it was in before, and at this point, astronomers still had no idea what this object was, and so in order to confirm the identity of the object, astronomers performed spectroscopy observations to determine what it was made of. Every material reflects light in slightly different ways, and more specifically, the amount of light that is reflected will differ at each wavelength. And so to determine the material of this object, astronomers took light measurements of the third stage at many different wavelengths, which gave them a spectroscopy graph. With this data, they could compare it to other spectroscopy graphs and see if it matched any other materials. And it turned out that it was very similar to the spectroscopy graph of white titanium oxide paint, the exact kind that was used on the Saturn V rocket. Astronomers were also able to trace the object's trajectory backward and found that it left Earth's orbit in 1971, and so with this information, astronomers could confidently say that this really was the long-lost third stage from Apollo 12. Astronomers continued to track the orbit, and after just a year it was once again thrown out into an orbit around the Sun. And calculations made by astronomers showed that it will return to Earth in the mid-2040s. Meaning this object will spend many more years racing through space, but the laws of physics will always make sure it returns home every now and then. This remarkable story demonstrates the complexity and precision required in space navigation, where even a small error of 40 km/h in velocity correction can send a massive rocket stage in a completely different trajectory than intended, resulting in decades of orbital wandering through the solar system. The incident highlights several important aspects of space exploration and orbital mechanics, including the delicate balance of gravitational forces at Lagrange points, the influence of multiple celestial bodies on objects in space, and the challenges of tracking and predicting the movements of human-made objects in the solar system. The fact that this third stage managed to return to Earth orbit after more than 3 decades showcases the deterministic nature of orbital mechanics, where given enough time and the right conditions, objects can find their way back to familiar territory despite being sent on seemingly chaotic trajectories. The use of spectroscopy to identify the object demonstrates the sophistication of modern astronomical techniques, as scientists can determine the composition of distant objects by analyzing how they reflect light at different wavelengths, allowing them to match the mysterious object to the specific paint used on Saturn V rockets. This case also illustrates the long-term consequences of space missions and the importance of proper disposal of rocket stages and other space debris, as objects that aren't properly directed into stable, out-of-the-way orbits can potentially return to Earth's vicinity years or even decades later. The story of Apollo 12's third stage serves as a testament to the enduring nature of human artifacts in space and the perpetual dance of gravitational forces that governs their movements, reminding us that space is not an infinite dumping ground but rather a carefully balanced environment where every object launched from Earth continues to interact with celestial mechanics indefinitely. The precision required in space navigation becomes even more apparent when considering that the tracking error that caused this entire situation was relatively small in percentage terms. Yet it was sufficient to alter the rocket stage's fate completely, sending it on a journey that would last longer than many human lifetimes. Furthermore, this incident provides valuable lessons for future space missions about the importance of accurate tracking systems and the need for verification of trajectory data. as even minor discrepancies can accumulate over time and distance to produce significant deviations from intended paths. The return of the Apollo 12 third stage to Earth orbit in 2002 also presented astronomers with an unexpected opportunity to study how materials behave after extended exposure to the space environment. As the rocket stage had spent decades traveling through the harsh conditions of interplanetary space, experiencing temperature extremes, micrometeorite impacts, and radiation exposure, the fact that the white titanium oxide paint on the rocket stage remained identifiable through spectroscopy after all those years speaks to the durability of materials designed for space applications and provides data points for understanding long-term material degradation in space. This discovery and subsequent identification of the object also demonstrate the importance of maintaining detailed records of space missions, as astronomers were able to match the object's trajectory back to 1971 and connect it definitively to Apollo 12 only because comprehensive documentation of the mission and its trajectory existed. The periodic returns of this third stage to Earth's vicinity, predicted to continue into the 2040s and beyond, create ongoing opportunities for observation and study, potentially allowing scientists to track changes in the object over multiple encounters and better understand the long-term evolution of orbits in the Earth-Moon-Sun system.